Okay, I think the people are joining. Hello, everyone. Welcome to this YT workshop. So I would suggest let's wait for maybe just 1 more minute for people to sign on. Good morning. Okay, let's get started. So hello again. Welcome everyone to join this YT workshop. So today's session will last for 2 hours. So if you know about this workshop from the PIRE webinar, this is a bit different than other PIRE events. And today's workshop will also be pretty hands-on. So Matt has a few slides, but then the after that it will be more instructional. So by default, most of the attendees, you're just attendees. But if you have questions, please raise your hand, and then I will promote you to become a panelist, so you can speak and ask questions. So it's our great pleasure to have Matt Turk, teaching us how to use YT today. Matt is an assistant professor in the School of Information Science, and he also holds an appointment in the Department of Astronomy at University of Illinois. So his research is focused on individual interaction with data and data processing. And so I will just let Matt go ahead and start the workshop. So.
Hi, folks. Yeah, thank you so much. I'm going to share my screen, assuming that's okay with everybody. And I have on this screen some slides. Every time I share my screen, though, it turns out that I need I lose the ability to see the participants. So let me see if I can quickly fix that. Oh, I always make such a mess of this. Okay, I guess I'll do without the participants and whatnot until we are all done. But good morning. So I'm gonna give an introduction to YT, and I want to start out by just saying hello and sort of taking a moment to I don't know if get centered is the right way, but just to say how grateful I am to have this opportunity. I'm gonna be sharing some stuff that I work on, but also share with you about how you might use it for your research. I will just say thanks for having me, and I'm really glad that we all have this ability to be here and to kind of be present for this. So there's a lot going on, and I'm really grateful that that we can take the time out to do this, and that the EHT has done such, or the EHT group has done such an amazing job of bringing so many cool workshops out there. Before I go too far, I want to take a moment just to note that even though I'm going to be the one presenting today, there are a whole bunch of people that work on the code that I'm going to describe, and specifically there's an executive steering council. So Britton Smith, Deacon Monk, John Zuhone, Stephanie Tonneson, Nathan Goldbaum, me, and Cameron Hummels. And then two folks that have been really active lately, Clement Robert and Corinne Cadu, have all worked very hard on the things that you're going to see today. And so I want to say thank you to them for letting me, for providing such a wonderful community for me to be a part of. I'm going to start out just a little bit with some ideas about the mindset that goes into YT, because that will help to guide how we think about data analysis. And I'm going to start out with the statement that we tell lies to visualize. And in fact, one of the ways that we think about this often, and I know this might seem a little bit out of the usual of what you're expecting for a technical talk, but I want to start out just by um, talking about how we take visual information and we bring it in, and conversely, how we take information and turn that into some sort of a visualization that we think of. So if I were to say the sentence, "The sky is full of stars that twinkle," we could break this down into several different components. There's the first one, so the sky, and we all have kind of a visual conception of what we think of when we think of the sky. It's full of stars, and so these stars, we all have a mental model in our mind of what a star is, and what it looks like, how we can recognize it, and various different properties we can infer from that, and they have behaviors that are associated with them. So they, in this case, they twinkle. They might get brighter and darker, in the sky, and of course there are reasons for that we're all very fond of describing. But this process of assigning meaning to pieces of information that are received in our eyeballs, or assigning perceptions or assigning um, visual representations to pieces of information that we know, is a process that we can think of as translating from fixed reality, from data into knowledge, and that's where we come in here. In some cases, in for instance, something like this, you've got the Orion Nebula. It's emitting light. That light gets transmitted, and we think about that in the perspective that you might have something, and you might have an object. That object is emitting some type of a light to an eyeball, and in this case, this is it's not my eyeball. I don't have green eyes, but it's an eyeball, and this light streams across, and then it somehow gets it impacts our rods and cones. It sends signals off to our visual cortex, and then we construct that information in our mind. And if we're doing this from the perspective of, say, simulations, what we want to be able to do is we want to be able to understand what's going on from a data perspective, and then from the perspective of replicating that information as it might be visible to an eye, in order to solve essentially the inverse problem of what could generate things that we see. We want to be able to have very high fidelity methods of dealing with and processing our data. Um, so this takes us to the notion of say, fluid dynamics, or of volumetric data, where you have data that is defined in every location, uh, perhaps not necessarily regularly, but it is certainly defined in every location. And from the perspective of simulations, you have various different phenomena that are evidenced in simulations that we can correlate to pieces of or to things that we see in our everyday life. And of course, this is a very familiar fluid dynamics and stability, and we know how fluid dynamics works. And so when we do simulations, we update our fluid dynamics equations on some, say, either regular mesh or through Lagrangian particles, or some hybrid approach. Um, oops. And so we allow our simulations to run over time, and then we update them, and we apply our time stepping updates in order to generate information, to generate data that we can then analyze and visualize in some way. And so this is the forward problem, essentially. It's that combination of the forward and the reverse problem that we really want to ensure that we are able to do. And um, YT thinks about this from the perspective of there essentially being four components to a vocabulary of volumetric data analysis. The first of these we think of as registration. The second of these we think of as transformation. The third one is some type of a selection procedure. And then the final one is a reduction, where well, I'll talk about each one of these individually. Um, the process of registration, particularly when we're thinking about data, is where we have some set of values or pieces of information that are laid out, say, on disk. And they're laid out in some manner that may or may not correspond to the actual spatial organization or the physical meaning of what something represents. So for instance, this might be a set of values that are just blasted out as floating point raw, little endian, let's say, onto a server or onto a disk somewhere. And that doesn't necessarily correspond to the spatial organization or even the logical organization of the data. Disks have sector sizes, memory has page sizes, and there are all these different things that get in the way that change how we have to represent our data. And so there's oftentimes a two-step process. So the first step of these, constructing a logical representation of our data. So transforming our data from some disk or operating system or storage system specific format into a logical representation that may or may not actually correspond to the physical representation. But then there's the second process of registration, where we take this logical organization of data and we transform that into a spatial representation. So this might be, for instance, transforming a logically Cartesian data set into a spherical coordinate system or a cylindrical coordinate system. The key underlying thing that this registration process does is it provides us an ability to query specific locations. So the main thing that we get out of this is the ability to define and then execute an f of x, where x is a vector and f is one or more different fields, so some type of a value. And if I think about this in the context of, say, the room that I'm in, if I have temperature sensors located at many different locations, those might be my sample points. And then if I define some type of a kernel that describes how to interpolate between them, that is what I would think of as this f of x. And of course, this is more straightforward to think about in terms of uh, uh, mesh-based data sets, for instance, where, say, things are piecewise constant within a given cell, or perhaps there is some complicated shape function in, say, a finite element mesh. But we can also apply this to particle-based or discrete sampling data sets. And in this case, typically, our data sets will be laid out in who knows what type of format on disk, but we can register them again for analysis by transforming them into some type of a spatial coordinate system. And then, say with SPH, we apply a sampling function that involves a convolution, either across the whole domain or with some cutoff point, like with the cubic spline. But this is the fundamental process of registration. It's taking data and then turning it into something that has spatial awareness, and where there is a defined function that we can apply in order to compute some minimal set of fields on disk, from on disk. So the second component of our process of data analysis is that of the transformation. And I kind of alluded to this a little bit just a moment ago, where you have, say, a set of primitive variables. So for instance, you might have a simulation code that solves for the density, the velocity, the energy, and so on and so forth. But those aren't the only set of values that are accessible. These can be combined in many, many different ways in order to produce fields that only exist in potentia. And I think that actually should be n potentia, but I'm not very good at Latin. I just thought that putting it in italics and spelling it that way might sound clever. So you can imagine, for instance, that in this case we have density, but we also probably solve for the x and the y velocity. Now, because we have the ability to register these data sets, because even though these are all registered identically, they don't necessarily have to be. But since we can register and we can apply queries at specific locations, that means that we can combine them in some algebraic way. So for instance, we might have the x velocity and the y velocity defined as well. And so I guess this would be the x, this would be the y. What we can do is even though we don't necessarily store on disk the magnitude of the magnitude of the velocity is something that can be computed. And so we can apply an arithmetic manipulation in order to get back out, say, the magnitude of the velocity. This is something that exists in potentia and is still true, but doesn't necessarily have to be written to disk in order to do that. The next step in our vocabulary of data analysis is that of the selection. And so you can choose to filter things based on, for instance, their connectivity, their spatial organization, or even based on criteria from one or more of their field values. And so this is once again our favorite fluid instability. And let's say that we wanted to select based on just a spatial selection. So we've got, for instance, this set of values that we want to select. And you can imagine that this geometric set of values then provides input into some type of later reduction, where we're doing, in this case, this is just a simple binning based on the level of resolution as I move it around. But this doesn't have to be a spatial query, and it doesn't necessarily have to be a query based on just field values. It can also be something based on connectivity, for instance. So if you have a set of particles that are all nearest neighbors, for instance, you could imagine a selection based on that. We can also apply reductions. And so reductions in some cases are interim steps towards, say, a remapping into a different registration. But reductions can also be, integrations. They can be computations of statistical values and so on. But we can apply these along axes, along paths, and even along non-trivial manifolds. One of my favorite examples of a reduction is, for instance, taking a test particle and integrating it throughout a domain and then sampling positions along the way. So for instance, this is a sampling of the density values as we progress through a simulation, and we're sampling on the right-hand side, and the inputs are taken there from the left-hand side as it moves. But this is the type of thing that, for instance, can be logically mapped onto the concepts of ray tracing, onto the concepts of advection, onto the concepts of accretion, and it can be mapped logically onto even things like a buoy getting moved throughout an ocean or an oil spill, and or I don't know if you ever saw the movie Twister, but there's a scene in there where they spray a bunch of stuff. Anyway, I was just thinking about that movie the other day, and it occurred to me that I haven't seen it long enough time. Oh right, this is being recorded. I should. Anyhow, the final thing that we can do with all of these different these different operations is the most important one, which is that of composability. We can compose these operations and conduct them in sequence in order to provide advanced workflows that really go end to end. So for instance, we might have a whole bunch of data on disk. We can register that data in memory, some logical and then physical organization of the data, where I want to emphasize the data doesn't need to all be sampled at the exact same locations or with the same resolution. So in this particular case, you'll see that there are multiple different embedded resolutions inside this one data set at different places and locations. We can then apply operations for selection and then reduction in order to, for instance, identify halos. So we can apply friends of friends finding or hop finding or something like that. And I know those are cosmological operations, but the same concepts apply elsewhere. And then based on the results of that, we can apply we can apply quantitative reduction in order to say, in order to identify, say, the mass or the virial radius, or say the velocity dispersion of these different objects. And then we can regard those as a distribution in a different non-physical space. So we might be able to construct, say, a mass function from those halos following that. And so it's this composability of operations where we're defining where we are defining our steps in such a way as to um, our steps in such a way as to preserve the semantic meaning of each individual component that allow us to really do complex operations. Okay, so I'm going to talk today about YT, and YT is a volumetric analysis platform. It's open source, it's community driven, it's written mostly in Python, although you will find scattered about YT and or you will find within YT itself a fair bit of Python code and a bit of C++ code. And you will find scattered about its associated projects code in Rust and in TypeScript, and I think there was even a little bit of Julia at one point. But YT is designed to be essentially a platform for analyzing and then as a side effect of that, visualizing volumetric data. It supports a couple dozen different data formats, and it is designed to work from the very big to the very small data. One example of what we try to accomplish with YT is we try to remove the need but not the ability to apply code or method-specific analysis. So as an example, these are different data sets from the Gamer2 code, and Gamer is a block-structured refinement code, Arepo, which is an adaptive Lagrangian Eulerian code with moving mesh, and then finally Gizmo, which is a meshless code, which is essentially represented as particles. The same script was executed on these three different data sets in order to produce the output visualization. And that script was pretty short. It was essentially a slice through the center of the domain. And while you are still able to access the underlying data in the raw format, you also have the opportunity to avoid that and think simply in physical coordinate systems or physically meaningful values, despite the fact that these codes are different and output in different ways, have different units associated with them on disk, and have different methods. So the mechanism for representing data within each one is different. I'll talk about that during our excuse me, during the interactive section, but essentially there is an underlying process of regularization that goes on, that if you follow that if a data ingestion method follows a certain set implements a certain set of operations, all of the rest of the YT operations are accessible to it. I want to step back just for a moment and say that YT is used for visualization, but it's much less a visualization engine than it is a set of components for constructing the inputs to visualization engines. So specifically, the most common platform for visualization that is used within YT is Matplotlib. YT deeply integrates with it, providing methods for supplying mesh visualizations and so on to it. And there are also three different categories of visualization that YT really tries to support. The visualizations that we make for ourselves, so the stories that we tell to ourselves, so exploration, for instance, of our data sets. The visualizations that we make for our peers, so things that might go into papers that we write and that we publish, and then also visualizations that we make for everyone else. People have used YT for volume rendering, for generating volume renderings that are both designed for outreach scenarios, as well as volume renderings that are designed for exploration. Each one of these different brings with it a need for narrative, for interactivity, for control, and for visual languages. And I'm not necessarily going to go too deep into that just now, but I want to talk about a couple of the common things that we do in YT. So one of the first things that I usually do with my data sets when I'm exploring them is I will load up a data set and then I will select from it. And then I will do something like an integration along an axis. So we're going to do this in just a moment, so I'm not going to belabor the point. But in this particular case, this set of 2 lines of code will load up a sample data set, in this case, isolated galaxy, and construct an integration over a region of the data set that is over the entire data set. So that's what this -r does. It will integrate density along the z-axis. And so you'll see over here, it says density grams per centimeter squared. I'll talk about the unit handling in YT in just a moment. What ends up happening on the back end, though, is the data gets selected. That's the ds.r. The index is collapsed into a quad tree and re-registered in a pixel plane. It's chunk by chunk loaded and applied to that resultant quad tree, and then it's used to create a 2D value buffer. So the reason that I'm going through these steps in what seems like more detail than is necessary is because operations like this, particularly for mesh-based data sets, are the most expensive part. Everything up to the dot plot is the most expensive part. And after that, there is very little need to touch the disk again, to do anything else. And you can interactively pan and zoom and generate lots and lots of visualizations very cheaply afterwards. And then finally, the data values get passed back to matplotlib. And if we zoom again, this doesn't require touching. Ooh, I hit end by mistake. Sorry about that. If we hit zoom, it doesn't need to select data again. It doesn't need to collapse it. It doesn't need to load it again. It reevaluates the quad tree and then passes that to matplotlib, but that's all. When we do things like loading a data set, so when we do things like selecting, say, from 0.4 megaparsecs over to 0.6 in code units, then we take a profile of density, temperature with a cell mass and no weight. It chunks across the data set after it identifies the region that you're interested in, and then it applies a histogramming process to it. It selects it, it computes the bounds, loaded and placed into the bins, and then it gets passed over to matplotlib as a 2D value buffer. So we're going to dig in now, and it's at this point that things are going to become a lot less formal. But I want to put up there just a thank you for coming to this. And additionally, there is a survey that you're to fill out. And if you enjoyed the first part of this, maybe you should fill it out now before I have any opportunity to disappoint you during the second part. But the link will also be in the chat. And that is the conclusion of my slides. And it's at this point that I am going to start working interactively with you. So before I go any further, I guess I should probably ask for questions.
Yeah, so everyone, please feel free to put question in Q&A, or if you raise your hand, then I will unmute you or promote you to a panelist so you can speak.
I've stopped sharing because I want to pop the chat out. So I will start back up sharing in just a moment. Oh, in potentia is great. Oh, great. Okay. All right. So then what I will do is let me start my sharing again. There we go. Yes. So I will answer this one live. So if you followed the installation instructions, what you will do is you will be able to it will automatically download the data with me. So the most recent version of YT has a method for downloading sample data that's built in. And so we're going to use that today, but I will also show you how to get the data in case you are not able to install the most recent version of YT. Okay, so I'm going to show you very briefly the home page of YT just so that you can see the data. If you go to yt-project.org, and again, you don't need to do this if you are using the Git installed version of YT. But if you go to ytproject.org under quick links, you will see sample data sets loaded by YT. All of the data sets that we're going to talk about today, and I think we will only do 2 or 3 of them, will be reasonably small, and they will be located on this website. The one we're going to start with is called Isolated Galaxy, and it is at the link that I've just put in the chat. But again, if you are going to follow along and you are using the live version of YT, then you will be able to do this automatically. So the first thing that I'm going to do is I'm going to import YT. Typically, when I'm doing this, I'll import NumPy as well, just so that in case I need to do some operation. But I'm going to import YT. And if you do yt._version, it should say something like 4.0.dev0. And hopefully, if you're not like me, you won't get this visible deprecation warning. It has been warning me about this for some time now, and I seem not to have taken its advice on getting rid of my old configuration file. So YT has at its top level namespace a number of different functions. Sorry. The one we're going to use first is going to be yt.loadSample. The way yt.loadSample works is that it has a catalog of available data set. So I did put the link in there. Here is the top level link to the data catalog, and here's the link to the tar-gz. And if you type,
I think you just the panelists, but don't worry, I will copy and paste that to everyone.
Oh, I was just sending it to panelists. I'm so sorry. I got confused with where I was putting it. I'm sorry. It's my first day. So if you do yt.load_sample isolated galaxy, it uses a library called Pooch to download it and cache it. You'll see here it says files located at this place, so it tells you where it's going to stick them, and then it will load them right here. Now, of course, I forgot to say ds equals, so I'm going to just restart and run it all again, just so that I've got a clean notebook. So typically, I call my data sets ds, and ds so the loading of a data set is designed to be as lightweight as possible. What that means is that in general, especially for particle data sets, but also for mesh data sets, YT tries very hard not to load anything off disk that it absolutely does not have to for the stage of analysis you are currently at. So in this case, this is a data set produced by the simulation code Enzo. And Enzo outputs a parameter file, as well as a hierarchy file, as well as individual HDF5 files. When we do the load sample operation, all that YT loads is the parameter file. So we're able to access information about the metadata, but anything that's not in the metadata does not necessarily get made available at this time. Now, mind you, Enzo is notorious for things like having an enormous amount of metadata in its parameter file. So if we were to look at ds.parameters, you'll see that it quickly fills up my entire notebook with all the different parameters that have been included. Let's just do a len on ds.parameters. And there are, in fact, 402 different parameters. I believe that since this data set was created in the early or in the late 2000s, early 2010s, this number has gone up considerably in the main branch of Enzo. But what it does do is it loads in enough information to, for instance, apply some diagnostics. So because this is a cosmology data set, it will have a current redshift. In this particular case, that current redshift is set to 0. But it will also have current time, so you can see how far along it is. And oh, that's interesting. You'll note that there is this is a type of unit quantity. We'll talk about that in just a minute. But there are other things that go in, and I want to make a brief comment about this. The philosophy behind YT is that you should have access to all of the information and all of the data that is available. But on top of that, anytime YT is able to interpret that data in some meaningful way, it will attempt to do so. So there is both the parameters. Oh, I'm sorry, I should have mentioned, this is called Jupyter Lab. So this is the newest form of Jupyter, which is an interactive notebook environment. If you want, you should be able to do most of what we're going to do on either the IPython command line in the Jupyter or IPython notebook, or just through the Python executable. You will have to swap out a couple things. So whenever I do a visualization, you'll have to save that to disk and open it separately. So for instance, here, if I were to type cosmology, is that the right thing? No, it's initial time. That's what it is. So you'll note that here I have access to the underlying Enzo parameter initial time. So this is our metadata. But YT also provides access to it in sort of a value added way. So I'm sure many or most or all of you are familiar with AstroPy units. YT has a unit system based on the symbolic math library SymPy. There are some reasons for this. The main one being that cosmology in particular, when applied to, or when utilized in simulation codes, requires a fair bit of flexibility in how we define things. Many simulation codes, which YT is designed for, when using cosmology, normalize to a floating point value that is with respect to the current redshift and the parameters of the cosmology that go into the simulation. So this is not a cosmological simulation, but it does have some of that embedded into it. The values on disk are normalized to have an average value of 1, but the translation from that into, say, grams per centimeter cubed is dependent on a number of different parameters. And so in a cosmology simulation, not all cosmology, of course, but in many cosmological simulations, the normalization factors are dependent on the scale factor at the present time in the code, as well as the omega matter, omega lambda, all these different parameters. So in order to get around this, we provide unit registries. So our current time, you'll note, says code time. This code time is not the same as the code time in a different simulation data set. And that's okay. But that's why we have to back this by the SymPy symbolic math library so that we can simultaneously analyze data from these different systems. We do have the ability to convert this to AstroPi units, and I think it's to AstroPi. Yeah, so you can convert to and from AstroPi units. So if you're used to that, that is something that you can do pretty easily. I'm not sure if they currently work with the initializers, like so if you just try to cast it as that essentially, but I think they might. Excuse me. So we can do things with this. So current time, this unit, and I'll just say this is T. This unit quantity has things like in units, and of course we can do, in years. And so that's, the in years. We can also do neat things that you're probably used to, like let's say that I wanted to divide that, yt.units.mpc divided by t. That's MPC per code time, and we can do other fun things like let me give this to me in CGS. When we load our data set, each type of data will either have a unit base that it prefers, or you can specify the unit base inside your initialization. So I don't actually remember if it works with load sample, but you can supply a unit base in order to get things back in some different base unit system. And that modifies, for instance, what, let's see, is it in base? Yeah, what it gives to you in base. Now, if we were to load it again and specify a different unit base like MKS, then the base unit system would be that. I can't remember if we have a whole bunch of others. I think I think that it's like we got oh yeah, different types of magnetic fields, for instance, can cause fun things. So there are a lot of fun tricks you can do with the unit base and whatnot, but the end result here is that we have semantic information, we have metadata associated with all the different parameters that go into the simulation. One moment. So I want to briefly ask, is anyone trying to follow along and having trouble doing so in a way that I could be helpful with? Okay, then I'm going to continue forward. So there are a number of different, excuse me. Oh, yes. So typically that's so that is an issue that we have seen when installing via, oh, yeah. So version 3.6.1, you will have to manually download the isolated galaxy data set. Yeah, pip installing YT won't get you that. So let me show you. So in order to get around using version 3.6.1, what you can do is you can download the data set that was linked to on, but that CK linked to. And untarring it. Yeah. So I will show you how to do this with downloading it as well if you're using YT 3.6.1. So what you can do is you can go to the YT project homepage, and then under quick links, sample data sets in YT. If you scroll down a bit, you'll see one that says isolated galaxy. I'm going to download it. I'm just going to put it somewhere that is specific to my EHT workshop stuff. So I've downloaded it, I move it, and then I untar it. You'll see that it outputs all this stuff. And then in my notebook, instead of saying load sample, I put the full path to it. And in this case, I also need to say Galaxy 30. Oh, did I get the? Oh, yes. So note that this is a slightly different command, and I'm going to put both in there. This one, load sample. But what I'm doing is I'm saying /home/mturk. So I'm providing the entire full path to it. And in this case, I also need to specify there's a subdirectory, which you might have seen here. Oops. Here's the directory I was in when I untarred it. And I specify the path to Galaxy 30. It should give you essentially the same thing, although you might see instead of unit quantity in version 3.6.1, you might see that something that says YT quantity. For all intents and purposes, they should be the same. Oh, good. I'm glad it works. Okay. So there are a couple places that I want to go from here. The first one is that there are a couple different pieces of information that might be of interest to you. If you have IPy widgets installed, you can do things like type ds.domain_width, and it'll pop up with something like this. So the domain width in code length is 1. Let's do it in MPC. Okay, yeah, AU, and so on and so forth. These are all, this is a pretty, what's an MIL? Not a mile. Mil? Anyway, we have the ability to, regard these things in different units. That I forgot that it was going to do that. And then there are also different pieces of information about the data set that you can examine. So domain left edge, domain right edge. There we go. If I put a comma on there. Now, at this point, we still haven't opened up any of these HDF5 files on disk. Now, I want to take just a second. You don't have to do this, but what I'm going to do is I'm going to say H5ls-R, and I'm just going to grab one of these. Isolated galaxy, oh geez. Isolated galaxy, galaxy 30, galaxy 30.cpu0008, let's say. You see, it's got tons and tons of these things on there, and they're all different shapes and positions and whatnot. And so we're gonna use YT in order to get access to those. Oh yes, YT does need Python 3 and above. So if we do ds dot index, it'll force loading all the data, or it won't load all of the data off of disk, but what it will do is it will load an index of the data. So it does this in what we think of as a lazy way, where it looks at the positions, the shapes, the sizes, and what's available, and then it tries to figure out what it can say about it. Now, we can do this implicitly by doing something like ds.fields. And you'll see here on mine, it says, oh, it's parsing a hierarchy. And then it spits this out. And if we look at this, this is, and yours may not look like this, and that's okay. This is just a browser for it that's based in IPyWidgets. If we look in this, we can see all the different fields that YT either found on disk or thinks that it can generate. In this case, it's an Enzo data set. And so if we look at the Enzo tab, these are all the different fields that it was able to find on disk. So let's see, H2 density. Oh, I see. There's their source. That actually just means that it found it on disk. These are the variables that go into our field definition. But you'll note that YT also has lots and lots of different values that are accessible that are not on disk. So for instance, if I go to the gas side, helium +1 mass, this is how that field is defined. This is our transformation grammar. So this is where where it's applying an arithmetic operation to the set of fields in order to compute them. Now, there are some variables that might go into this, and if we look over here in the variables tab, we can see what those variables are, so that we can actually, figure out what is going into it. But here in our source, we can see how it would compute that. And so in this case, it for the helium +1 mass, it would compute our our helium +1 density, and multiply that by the cell volume. There are also some index fields here, and these are things that become useful. So for instance, cell volume, this is how you get the cell volume for this particular field. And I want to note that this is specific to the geometry. I'm going to take a second to show something that I had forgotten that I should do. If I do fake AMR dataset, let's do geometry equals cylindrical. And I do ds2.fields. Now, if I look at this field, you'll note that my cell volume for a different geometry is defined differently. The volume is defined in terms of dr, d theta, dz, because it's a cylindrical geometric form. YT is geometry aware, and so it is able to utilize that information. Also for things like the path element. So the path element along theta, which doesn't necessarily exist along here. Path element x Y, and Z, for instance. But these are all the different fields that YT thinks it knows how to generate from this data set. And it does that by looking at what fields are existent on disk. It looks at a set of field plugins for things like magnetic fields, for things like fluid fields, and for energy fields, for astrophysical fields. And then it says, given this set of fields that I have on disk, can I generate this field? And so if it does, then it thinks that it can generate them, and so it provides them. There are also different field types for things like particles, so the n-body particles that are in the system, and then also deposition fields, so taking particles and sticking them onto a mesh via different methods of interpolation or sampling. I can tell that I am talking too much because my coffee has gotten cold. So the next thing that we're going to do is we are going to make a straightforward projection plot. One of the things that I'm working with a student on, so Sam Walkow is a PhD student that I work with. We're working on identifying all the different pieces of grammar, basically, that we use and jargon in YT that are astro-specific. Projection is almost certainly one of them. A projection is an integration along an axis. And we can take a projection along an axis and generate a plot from it by creating a YT projection plot of our data set along an axis and of a field. We've assigned it to the variable P, so I'm just going to display P here. So this has loaded our density, it has projected it along an axis, and then it has returned it to us. There are a couple things that I talked about in the introduction that are now happening. Our fields are loaded from on disk. They are converted into a unitful array. They are then multiplied by the path length along the axis we are projecting along. And then they are sampled at regular intervals. And we can zoom in, and all that happens between these, all that happens, so if we zoom in by a factor of 10, what happens is it resamples them, but it doesn't reload anything from disk. So far, this is not super fancy, but what's happening here is, but this is sort of the old way of thinking about doing a projection in YT. There's a lot of implicit stuff that happens here, like the data selection. Let's say that I want it to be more selective in how I generate this projection plot. Every data set has what's called a region selector associated with it, a region expression. Oh, yes. Then the field that you want to project. Now, we could also project, say, temperature. But that doesn't make a lot of sense because now we're taking our Kelvin times centimeters. We can, of course, do, say, a weighted average. That makes a little bit more sense. This is the density weighted temperature at all these different positions. But we've also got different methods. So we could do a maximum intensity projection. And this is the maximum value of temperature at every single location. You'll note that there are some hot spots in there in this that we aren't really doing much with. There's projection, there are different projection types. I'm gonna go back just for posterity's sake and leave this as projection of density. I'll also note that stuff like color maps and whatnot, this is the default YT color map, but of course we make access to all of your other favorite color maps So for instance, we bundle things like a couple other ones like dusk. I think we also bundle octarine. I don't remember if we ended up bundling hypnotoad. Nope. You have access to all the matplotlib ones, of course, and then if you're in a really like VGA palette kind of mood, you can also use the Doom color map, which is just a straightforward mapping of the Doom default palette. But let's go back to our basic one, which we call Arbra. And of course, all the matplotlib ones. So if you like Viridis, and I don't know why you wouldn't like Viridis, it's pretty awesome. You can do that. The ones that we ship by default are also designed to be CVD friendly. I'm going to again step back from the visualizations. You can also do slice plots and whatnot, but I'm going to talk about our method of selecting things. So the dataset object has a bunch of different selection methods that hang off of it. So for instance, you could choose a sphere. So let's take a sphere which accepts two arguments, the center and the radius. And the center can be not just a coordinate value like 0.5, 0.5, 0.5, but you can also supply a string constant such as C for center, or you can say max. And in fact, if you supply a tuple to it, you can say max of density, which is the default, but you can also do max of temperature. And then the next argument to it is a radius. The radius can be either a raw floating point value, in which case it will be regarded as encode length. It can be a tuple, and if it's a tuple, the first value will be the quantity and the second one will be the unit. So I could say 1.0 MPC. And it could also just be a unitful quantity. So if I wanted to pull something out of a reduction from a different area. For this particular case, we'll just do, let's do a radius of 0.1 encode length with centered on the maximum value of temperature. Oh, I guess I can't do max of temperature yet. I'll have to deal with that later. We'll do it at the center. Let's do max here. So this is the most dense value. You'll see that it's going out. It's computing the maximum value. And now we've got a sphere. So this sphere is centered here. For some reason, this printed in centimeters with 2 cmcm in it. I don't know why. And with this radius in centimeters. We can now either, if we wanted, access all the values that are within that sphere, look at them individually, and we're going to do that. And this gives us a unit array. It's one long flat array. It has units associated with it. We can change those units just like you might expect. So we could do msun per mile cubed and gives it to us there. We can also do stuff like, summing them up, and it gives us to it unitly and, whatever. But that's not necessarily the most efficient way to access things. So until we query the data, it still lives on disk, or it doesn't live in memory. This sphere is essentially an empty vessel waiting for data to be poured into it. If we were to do this on an extraordinarily large data set, just calling sp.max, as long as we supply something like C, doesn't load any data from disk. But we can now conduct various different operations on it. And because we aren't loading the data manually into memory, YT can handle things like ensuring that we're not overloading data so that we still have RAM available. In fact, I do this stuff on, and in fact, we do our best to keep the total memory usage very, very low, unless you explicitly ask for a large amount of memory to be used. And so we provide some array-like operations. We've got stuff like max of density. If YT is able to, it will sub-chunk our data out and apply reductions to the final version. You may be familiar with the library Dask. Right now, YT does not utilize Dask. However, we are actively developing in a branch that we humorously refer to as the Daskening to replace some of our MPI parallel code with Dask as its underlying engine. If we just ask for the maximum value of density, for instance, it returns that to us. But like all good NumPy type operations, we also can say, why don't we take this along an axis? And so if we say we want to project the maximum density along an axis, we can do that. You'll note that it returns to us a projection object. I'm going to go ahead and plot that. You'll see now it has taken the density within our sphere, projected it along an axis, and then returned to us a plot of that density. Now, if I just do P equals, it automatically dumps the thing back out. Now we can do other stuff too. Like we can say, give me the argmax of density along the axis of temperature. That tells us what is the maximum temperature value, or what is the temperature value at the maximum value of density. So this is the NumPy operation for locating the maximum value, and we say which axes do we want to evaluate it along. We can do the same thing with argmin. Let's say that I want to do density axis equals velocity magnitude. It'll compute the velocity magnitude at the minimum location in density. We can't plot that one though. We can also do our usual stuff. So you can do the mean value of density, and by default, it just does the arithmetic mean, but you can also weight it. So weight equals, for this case, let's weight it along the cell mass. So that's our cell mass weighted mean density. But let's do density weighted by density, and let's project that along the y-axis, and then let's plot that. So this is the density weighted density along the y-axis after we've then plotted it. So we've started to see some of the different selection operations we can do. YT has selection operators for spheres, for cylinders, for rectangular regions, for I don't think we have toroids exactly yet, but we can also do some fun stuff with selection operations. So let's say that we're interested in looking at the corona around a galaxy, like this galaxy. So we've got this sphere. Now let's make a bigger sphere. So that sphere was a radius of 0.1, right? Let's say sphere 2 is ds.sphere. We'll center it on the center. And this time, let's make it 0.15. Okay. And now if we do SP2, and let's make a visualization of the exact same thing we just saw. P2 is equal to SP2. We'll do the mean of density along the y-axis, and we'll plot it. You'll see, yeah, it looks just like that one, only it includes a little bit more, right? We can do a variety of different arithmetic operations and logical operations on these things. In particular, what we're going to do now is we're going to take sphere 2 and we're going to subtract sphere 1 from it. And we'll call this our shell. All of our operations that we had seen before now work with our shell. We can also do, for instance, let's just do an integration of density along the x-axis. And so now this is our outer shell minus our inner, or our outer sphere minus our inner sphere integrated along the x-axis. And this will be a little bit clearer if we do, for instance, a YT slice plot, ds, we'll do it along x, density, data source. I just hit tab so that it would tab complete, but it's not. So this is a slice through that shell, for instance. So we can do different logical operations on our selections in order to very finely grain our the data that we want to analyze. We can also do selection operations, so that, for instance, exclude above. So let's exclude all temperature above 1E4 Kelvin. This gives us what's known as a cut region. Excluded hot is equal to that. And then we can do excluded hot, and let's just do the max value of temperature along the z-axis. You'll see there it is. You'll see it caps out right at 10 to the 4. There's an awful lot of stuff at 10 to the 4 in this area. I'm going to do the mean. There we go. That shows it a little bit better. So we can do a fair bit of selections, interaction between different selections, and then visualization in a spatial dimension of those different selections. But we can also, oh, and I should note that there are a number of different operations that we can do on this, like exclude above, exclude below, exclude equal, exclude inside, and so on and so forth. And there are also include that we can do. Each one of these plots also has different annotations that can be applied to it. So you can annotate, for instance, all of the grids. And that makes sense for this data set because there are grids in it. And you can see the different grids and their structure and how they are organized in there. And you can also do other, and these annotations are now zooming and panning and moving around aware. So now that I've annotated the grids, if I zoom in by a factor of 2, they are all registered, and those annotations will follow my zooming and panning around. The same thing is also true for things like annotate velocity. So these velocity vectors utilize the same data source. So they're using the same method of averaging or subselection or whatever. And they will follow as I move and I zoom. Oops, that was the wrong one. P4.zoom3. They will follow around. Now I've just shown zooming, but I want to point out a couple things. YT will try to guess the most appropriate unit. You can also set the units for your color bar You can set the units for your spatial positioning as well. You can also set the origin. In this particular case, I think the origin is set to the native of the coordinate system, but we've got this like full domain specific language that you can use. But here, let's do set origin. Let's do left window. Did I do something wrong here? Is it window left? Maybe it's just window. Yeah, so we set the origin to the origin of the window, and you'll see there it is. Maybe it should be window center. Maybe it's just center. Origin -1. Center window. Oh, thank you. Oh, yeah, CK sent this just to me, or just to the panelists, but CK figured it out. It's center dash window. And so now it's here centered in the center. And we can do other fun stuff like P4 dot set axis unit to mile, right? So it of course utilizes matplotlib for a lot of these things, but we're changing the units that go in, but we allow for doing this in a way that really hopefully makes sense. So this is a set of the spatial visualizations that you can do based on the information that is stored in the data file. We can also do non-spatial visualizations. So for instance, the profile command. This is another case of having a bunch of domain-specific jargon embedded. A profile in YT speak is an average along 1 or 2 dimensions, or an accumulation along 1 or 2 dimensions. So for example, if I take a density temperature profile, if I take a profile along density of temperature, and I can say, what is my weight field? Let's say cell mass, and I plot it. What comes out, and it's cropped there, is as a function of density, which is our first argument, what is the temperature value averaged with a weight of cell mass? Now, in principle, we can also do supply multiple arguments or multiple fields to our first value. Velocity magnitude, and then give it a weight field of cell mass. And what we see here is the average velocity magnitude as a function of density and temperature as weighted by cell mass. Now, what happens if, for instance, we don't specify a weight field? Well, then it, oh, you know what? It actually does know that you want that by default. Never mind. If we were to do a profile of cell mass, it will accumulate the cell mass in each bin. We have to specify a weight field none by there. And so now this shows us not the average, but the total accumulated cell mass in each bin as a function of density and temperature. Now these plots also have annotations that are accessible to them. So for instance, they have, you can overlay the average value. So in this case, collapsing this to 1 dimension can sometimes be a little bit tricky, or not tricky, can sometimes not produce the results you think by looking at it. And so you can have YT do the same thing and then provide the result as an overlay to it. The next thing that I want to cover is this notion of the region selector, or the region expression. The region selector is an object that hangs off of our dataset object and that accepts slice notation. So if you've used NumPy before, you're probably familiar with slice notation. The region selector is designed to be very similar to mgrid. mgrid in NumPy, remember, is a way of, and I'll show you mgrid. Mgrid lets you do, for instance, : 10. Sorry, :10, then it gives that to you, : 10.5. See, it sticks them into integers, but you can also do things like mgrid 1.0 to 20.546 with a fixed number of step sizes, and then it divides it all out, and it figures out, and it gives you an array. You can even do this in multiple dimensions. So 0.0 to 0.5, 256J. See, it gives it back to me in a two-dimensional array where it varies along each one of the dimensions. So the ds.r allows you to specify a left edge and a right edge along all three of your axes. And it also does, I think that the region expression doesn't work as you might expect with two-dimensional data. You can still do all of the operations. You just can't use .r to do it. And the default thing that R returns, if you just say ds.r and give it a colon, is it returns to you the entire data set. And so if I were to say ds.r : integrate density along the z-axis and plot it, that is identical to a projection plot of density along the z-axis. So this is a slightly different way of saying it that emphasizes the data selection process. Now, let's say that instead I just wanted a zoom in on the very center of it. And looking at this plot, looks like it's about 0.45 to 0.55 in megaparsecs. So I'm going to say 0.45 to 0.55. And I'll do that along all three dimensions. And so now you'll note that it automatically zoomed me in because it can do that because it knows a little bit about stuff. With spheres, it's not quite as able to do that. It automatically zoomed me in, and both the data that went into the projection as well as, because you'll note that I also sliced along the Z, so less data is going into it along the Z axis. It changes both what goes into the visualization as well as the bounds of our output image. We can do this in, you'll note that there I used code units by default. I could also do something like, I want to go from 400 kiloparsecs to 600 kiloparsecs along X, and let's just take everything along Y and Z. And I want to do the mean of density along the X-axis with a weight field of density. And now I've got the, you'll see that it did everything along the X-axis. It restricted it. but then it, it did it like that. Now, if I were to do axis Z, we should see, yeah, it tries to fix the aspect ratio, which doesn't always work. We can also do stuff like ds.r, and if we just slice along one axis, it'll return to us a slice through that. And then we can query that slice the same way, but we could also just do plot density on it. And it'll give us a slice plot at 0.5. If I were to do something cool like 0.2 to 0.8 and do a plot, you'll see that it also subselects the data that goes into the slice there. One of the most common things that people want to do with YT is to get data back out. And we can do that using the region selector pretty easily. For instance, I can do a slice. You remember that returned to me a slice object? If I specify a step size, this says give me all the data along the x-axis, and I do 128J. This is similar to the way that NumPy mgrid works. If you supply a complex value, and J is a complex value in Python, so if we do 1J times 1J, we get -1 plus 0J, so that's J is how we specify imaginary numbers. If we specify a complex step size, YT will regularize the data. This gives us a fixed resolution buffer. And so if I access it, it gives us a two-dimensional buffer of data where it has taken our variable resolution data, deposited that exactly the same way that it would in order to make a visualization, and given it to us. And I can prove that to you if I import matplotlib as PLT, and then I say, here's my row, and I say plt.imshow row, origin equals lower, just to be simple, I'll say log 10. You'll see this gives me a 128 by 128 image. So it's lower resolution than this one, but it has uniformly sampled it. This can be saved out to disk pretty easily, so you can you'll see it's a NumPy array, and you can save it any way you would normally save a NumPy array. We can do this in 3 dimensions as well. So if I wanted to extract a fixed, so let's say that I wanted to look at the data just within 4.7 to 5.3. You'll see this gives me, oh, sorry, that should be region. This gives me a YT region. And if I access data in that region, it's a flat array. The reason that it's a flat array is because not everything has the same size in it. And if I look at DX, for instance, this gives me the cell size. You'll see that not all the cells have the same size. They do have positions. So in principle, we could reconstruct it. But YT can also regularize this data for us into a 2-dimensional array. And we can do that by saying ds.r. And along 3 dimensions, let's say that I want that to be 256 by 256 by 256. I can supply a step size. This returns to us what's called an arbitrary grid, which we can query for data. And now if I ask for density, it gives me a 3-dimensional array of density that's 256 by 256 by 256, where it resamples inside that domain. I can also ask for things like derived fields. So say velocity magnitude. And it samples the velocity magnitude field. at all of those individual locations. So I've talked a couple times about derived fields, and I've mentioned that YT provides a lot of them, and it does, but it does not provide all of them. What I'm going to do is I'm going to show how to add your own derived field, as well as how to enable derived fields that YT does not enable by default. But before we do that, I need just a moment. I will return in just one moment.
Yeah, so in that case, maybe everyone can take your break. So we will be back in a few minutes. So Hangdo, I guess you raised your hand. Do you have a question? I think I unmute you already, so so you should be able to talk.
Hello, can you hear me?
Yes.
Okay, I have a question. What if I have a pandas data frame? Can I use YT with this kind of data structure?
So that's a good question. It kind of depends on what is in the pandas data frame. YT is really designed for data that is organized along 3 dimensions, whether those dimensions are Cartesian or not, but where there's a metric that can be applied. We are very close to having a full X array importer, which is labeled data sets along multiple dimensions. With pandas, if you have a set of discrete X, Y, and Z values, or R theta 5 values or something like that, and then a number of different rows, yes, you can use YT absolutely to do that. What I would like to do is show a little bit of derived fields, and then I will spend a moment showing how to load arbitrary data sets into YT, if that's okay. That's a great question, Vasilis. Yes, you can export in VDB. You can export in OpenVDB. The package that does that, I want to say, is called Ytini, because it's supposed to be YT with Houdini, something like that, because Houdini can import VDB packages. But yes, you can export in VDB. VDB is a pretty interesting project too. I didn't really know about it till I saw the DIBS seminar on it a couple of years ago, and it was just blew my mind. So I'm going to show derived fields, and then what I'm going to do is I'll show how to load arbitrary data, and then I want to end just by talking about some of the things we've been working on, which I may or may not actually demonstrate. So derived fields are one of the things that I like the most about YT. And in fact, they are one of the things that that are oftentimes provide the most value add. I actually am not a paleontologist, but I have been assured that there is a direct translation for the density and temperature into dinosaurs. So it turns out that if you take the density at a location and you multiply it by the temperature, that gives you your dinosaurs. So in principle, we could define a function that might take a field object, which in general doesn't get used, and a data object, and returns its density times temperature. And in fact, we can then do something like yt add field. And what yt add field takes is it takes a name, so dinosaurs, the function. I'll change the name of this to generate dinosaurs. And then by default, the sampling type is probably going to be cell in this particular case. And then we can add that to our global registry of fields. Unfortunately, one of the shortcomings that this has is that it only applies to data sets that are loaded afterwards. So what we want to do is we want to make it available into our Galaxy data set. So instead of saying yt.addField, we say ds.addField. And so now if I do dsr, of course that didn't work. Oh yeah, of course. Units equals k times g per cm cubed. Sorry about this. This is so embarrassing. I mess one thing up and then it's going to take just a moment for it to load everything. I'm going to rerun it with the kernel setup. See, it's doing an awful lot of data stuff just now. I guess it would be kind of a miracle if this all executed all the way down without any errors, right? It did. So I've defined a field, in this case, generate dinosaurs. I've added it to my data set, and I had to do a little bit of monkeying around with this units equals, and then I've accessed it inside that data set, and it generated for me my output field. Now, there are a bunch of different things that you can do. This right now is a fully local field. It doesn't require any information from the global values and so on and so forth. You can use field parameters, and those field parameters can be one or more dimensions. They can be a set of quantities. And so in some cases, this has been used to say, set a field parameter, which is so one thing I have done in the past is I have computed the angular momentum vector as a function of radius from the central point in a halo, and then supplied that vector of n by 3, where n is the number of sampling points, to a projection or to a phase plot or something in order to compute the average deviation from that angular momentum vector of the local gas parcels. So you can use derived fields to do some pretty complicated things based on either scalar or vector or even tensor quantities. And it's pretty fun to get pretty deep into it. There are also spatial fields that you can add. So we can add gradient fields to our data set. So for instance, if I wanted a density gradient field, I can say ds.add gradient fields density, and it will return to me the names of the fields that it was able to successfully add. In this particular case, it added a gradient x, y, z, and magnitude. And now I can say yt.slice plot, not slice bloot, of ds density gradient x. Oh, and I need to specify the axis first. So z density gradient x. I probably should have tested that before I just did it, huh? Oh, I know why, because everything is just, yeah, if I do density gradient x, because this is all uniform out here. So let's zoom in by a factor of 25. This should look a little better. Yeah, the color bar is still messed up. So that'll be a bug that I file on the repository. But we do get a density gradient here. Well, maybe if I zoom in a little bit more. Yeah, color bar still messed up, but well, that was sure embarrassing. I'm glad this isn't being recorded. You can still access all these different things, even though the color bar is messed up, and you can get a look at what's going on in these different areas. Sorry about that. My mic automatically turns off. My headset turns off if I don't get audio input for a little while, and the music I was playing ended. So you can add gradient fields. You can also add divergence fields, I believe. Maybe not. You can add all these different things, smooth particle fields and whatnot. But the point behind this is that gradient fields, YT will know that it needs additional zones in order to apply a stencil. And it will compute them through a cascading smoothing process, starting at, if you're using AMR data set, it will use a cascading smoothing process where it starts at the coarsest levels and then it applies in a recursive fashion in order to get good values in order to compute the stencil. The last thing that I want to show is how to load arbitrary data sets. So we already saw the load sample command, but we also have a bunch of other load commands. I've focused exclusively on mesh-based data during this workshop. YT has support for particle data. And in fact, in the YT4 branch, we merged what we thought of as the demeshing branch a while ago. And it destroys the notion of a global mesh in YT. And for particle-based data sets, it computes a hierarchical bitmap index of particle locations in order to optimize smoothing processes, sampling processes, geometric cutouts, and whatnot. You can also load in you can load in pretty straightforwardly hexahedral meshes, so hexahedral data sets where you might be stretched in one or more dimensions, as well as unstructured meshes, so tetrahedra, hexahedra that aren't logically organized, or axially organized. But YT also has support for loading arbitrary adaptive mesh refinement grids, octrees, and uniform grids. And the first thing I'm going to show you is how to load a uniform grid, because while we provide front ends for lots and lots and lots of different types of data sets, so Ramses, Enzo, Flash, Gadget, Arepo, Gizmo, AMRX, Castro. I'm spacing. You may already have a data file format. Maybe your data isn't so big that you're too worried about the parallelism of it, because perhaps you're computing things that are way more complicated and you don't necessarily need the bit, whatever. You can load data in using the yt.load uniform grid operator function. And this takes a data set, some domain dimensions, some units in order to really register the data, and also things like the current time, the periodicity, and so on. So let's say that I had a uniform grid that I wanted to load in. So let's say that I have a data set that's stored in HDF5. I will do with h5pi.file home mturk dicom.h5 mode R as F, F, we'll just do data 016, my values equal to that. Oh, I actually want 7. Now I've got my three-dimensional array. It's mostly 0 everywhere. What I can do is I can say yt.load. Oh, and let's do my values shape. yt.load uniform grid. And if I provide it a dictionary, and I'll just call this, what do I usually call it? Responsivity. My values. And then let me make sure that I've got the arguments correctly. Yeah, domain dimensions, length unit, bbox. So domain dimensions, let's say domain dimensions equals my values dot shape, bbox equals 0.0 to 1.0, 0.0 to 1.0, 0.0 to 1.0. And then let's do length unit 10 centimeters, let's say. This will load it into YT. List indices must be, oh, right, this has to be an array. And so now I've said the length unit is 10 times centimeters. So DS3 domain width. In code length, it's that. But now if I look at it in centimeters, the code length is 10. I can now do things like ds.r all, and let's integrate the responsivity along the axis of x and plot it. You can see this is very clearly a head. And we can do, let's do max. So you can start to see that we can load our data sets up pretty easily into our into memory. One thing that I haven't really shown, I will show now, is I'm going to clear the output from this cell. You can also load in data sets that are in, yes, I will. You can also load in data sets that are organized differently. So geometry like cylindrical and so on. Shoot, where are my notes on this? Anyway, I'll show you what it would look like if this data set were loaded in cylindrical coordinates. So let's do 1.0, and then here this will be r z theta, so 1.0, and let's do this one be np dot pi times 2. That should be ds4. But now I can do stuff like ds4, yt dot slice plot, ds4. Let's do an axis of z and responsivity. And so now you can see this reinterprets our data in a cylindrical coordinate system. It does an actual remapping of the data and then a resampling. So I know this doesn't look like much, but I'm actually, I know we're at the very end, so I didn't want to, I figured I wouldn't experiment too much. Some of the other stuff that that YT does includes, I think I got my singular plural there mixed up. Volume rendering. So there's a software volume renderer that runs exclusively on the CPU. There is an interactive volume renderer that runs on the GPU, and I will actually pull that up in just a second. We also have been doing some visualization using WebAssembly, so pushing reasonably sized data sets to the Jupyter kernel, the browser, in order to make the interactivity a lot higher. So we've been working a fair bit on getting our interactivity to be a lot more meaningful. I am going to take questions while I attempt to pull up the volume renderer really quickly, and then we will, I think, conclude.
So thank you very much, Matt. This is a great section. So do people have any questions? You can just raise your hand and I will unmute you. Or you can also type in the Q&A. So while we are waiting for people's question to come in, so Matt, I do have a question for you. So I look at the list, I will say maybe 1/5 of the people are probably from the EHT. So we are very interested in doing data analysis for GLMHT simulation where the metric is not flat. So if you want to make YT support that, what will be the most efficient way to do it?
So let me show you. So this is the volume renderer, the interactive volume renderer. I'm not going to belabor the point. So let me briefly. So inside YT, we have what's known as a coordinate system. And the coordinate system lives in between the disk and the spatial representation, and that's essentially how we deal with things like cylindrical coordinates. What the coordinate system does for us is the coordinate handler. Is it converts from our logical coordinates into the spatial coordinates. And I'll answer live in just a moment. This has been done to do things like geographic coordinates and so on, but essentially what you would need to do in order to implement this, and this is something I'm very interested in doing because it it also has relevance to, say, atmospheric data sets where one of the dimensions is pressure, and we want to be able to convert that into a spatial dimension, is we would implement a path unit, and then we would implement a mapping between wherever the logical, whatever makes sense with respect to the logical coordinate system and whatever you would like the output coordinate system to be. So it's a reasonably straightforward process as long as we have a functional form for the translation you want to implement. So as long, and it doesn't have to be an affine transformation, doesn't have to be a linear transformation, just whatever the transformation is. If we can come up with a functional form for that, it's reasonably straightforward to do. We also probably would want to disable fields that you wouldn't necessarily want to have. So a question was asked about loading a spherical coordinate with coordinates with logarithmic radial space. Right now, it's not great, but that's something that someone is working on right now. So Clement is working on that right now, and I'm collaborating with him on making that a lot easier to do. Right now, what you would do is you would load it in as a hexahedral mesh, and that hexahedral mesh would, in spherical coordinates, should be able to be sampled and visualized and so on. Unfortunately, there are a couple things that hexahedral mesh doesn't support. So what we're working on is we're working to fix that. I don't know what multi-order coverage maps are, unfortunately. I'm sorry to confess.
Maybe I can unmute Peter so he can explain a little bit. Just a second. Let me. Okay, I find you. So Peter, are you able to talk now?
Can you hear me?
Yes.
Mm-hmm. Oh, I could hear you for a moment.
Yeah, sorry, I had a hard time finding the button. No, it's like just a probability map that is arranged, but anyway, I will look it up later. Thank you.
Oh, okay.
Okay, any other questions? So if not, then again, thank you very much, Matt, for doing these 2-hour sections for us. And
Thank you.
also, also thank you everyone for participating. So let me just put the link again to the survey. So please fill that in, and then that will help us improve your future webinar and all that. So thank you very much. Okay, and yep. So there are a couple more questions in the chat.